Hello folks, today in this video we're going to talk about the conservation of momentum. We're going to be able to determine the change in momentum for objects in a collision. So conservation of momentum. The simple statement is that momentum in a system is always conserved. Now, conserved, what does that even mean? Like what's the point of it? You might have heard of conservation before in chemistry. Things like mass and charge and energy are all conserved, which, by the way, those are also true for physics. Chemistry is just physics applied to electrons. But momentum is one of the new ones that maybe you haven't heard of before that is actually conserved. What that means is the total momentum before an event will equal the total momentum after an event. And this is like a universal law of the universe. In fact, from what we understand, the total momentum in the entire universe is always been the same. And it will be the same forever. That's really weird. But that is how the world seems to work, that momentum is a conserved quantity. And that is definitely something that kind of takes a little time to get used to. But that is what it means. Now, that doesn't mean that something can't change its momentum, right? I can have a car and I can get it to accelerate and it will increase its momentum. What that means is something else, though, has to have a corresponding decrease in momentum. So if you get some momentum from somewhere, it's got to come from someplace else. So one particular method that momentum is transferred is through collisions. And of course, this is the thing that we've all seen before, right? Car crashes or whatever type of collision, billiard balls or whatever, what have you. Collisions are the biggest thing in our lives that we see momentum go from one place to another. So we're going to take a look at how we actually analyze collisions here. So mathematically, this is the equation that's in your reference table. Momentum before equals momentum after. And really all you do here is you add all the momenta for each object before and after. And so I find it's a little easier to write this equation if you think about, okay, I'm going to do all of the objects and list them out here. So P before does equal P after, but what I'd really say is, well, let's say you have a two-object collision. It's the mass of the first object times its initial velocity, so VI1, plus M2, mass of the second object, times VI2, and that's got to equal mass of the first object times its final velocity plus the mass of the second object times its final velocity. Now, you, of course, could expand this to any number of objects, but for our purposes, that's a lot of work. We're just going to stick typically with two-object collisions. So the equation for this is M1 VI1 plus M2 VI2 equals M1 VF1 plus M2 VF2. Now, before we actually start looking at some examples, I want to talk about two different types of collisions here. You've got both elastic and inelastic collisions. So in an elastic collision, not only is momentum conserved, but kinetic energy is also conserved. And what this really means then is that the objects kind of bounce off each other. Really, really great example of kinetic collisions or elastic collisions, are actually gas particles. So an ideal gas has elastic collisions between all the objects. There's no loss of total speed of those objects. That would mean the temperature would drop if it did. So as you would imagine, kinetic energy is conserved. But there are definitely collisions where kinetic energy is not conserved. Imagine two cars just, boom, crash together and stop. Well, they obviously had some energy beforehand, kinetically wise, but that energy is now gone, right? It's not in there anymore. So in inelastic collisions, kinetic energy, I'm going to abbreviate it as KE, is converted to thermal energy or some other type of energy where that kinetic energy is now lost and it's turned into another particular type there. So you got elastic and inelastic types of collisions. Now, what that's going to do is help us kind of understand that there are really only three types of different collisions that we're going to see. The first one is when two objects just bounce off each other and go the other way, and that is an elastic collision. So this is two objects bounce off each other. You've also got what's called a perfectly. I'm not going to use the word perfectly. Perfect is not a good word. Nothing in life is perfect. So we're not going to use that one there. We're going to call this one instead. Sorry, my pen is acting up on me here. An inelastic collision. And in an inelastic collision, we're going to say here that the two objects stick together. So those two objects can then come together and then start moving as one. You imagine that somebody catches, like a runner catches a ball, and that is now in that inelastic collision where kinetic energy is not going to be conserved. They're going to stick together and then keep on moving in some way. The other type is you got an explosion. And in an explosion, two objects at rest start moving. And what's really cool is that conservation of momentum helps us kind of understand how an explosion can work, right? If I have two objects just sitting here and then they explode, they both can't go the same direction because then momentum would be conserved. You'd have momentum just coming out of nowhere. So the key here is in an explosion, the two objects have to go opposite directions, which is really neat. If you've seen some of these new space movies, we've got things like Gravity or The Martian, famously. If you're in space and you have no way to move around, there's nothing to grab onto, you can actually use an explosion to help you. If you throw an object forward, well, by Newton's third law, you have to then move backwards. And so that's what's kind of captured here in this idea as well. Okay, so let's go ahead and take a look at some examples. So some methods to solve. There are really two methods I find that help students. One is called the momentum table, and one is just simply using the big equation. So I'm going to introduce you to the momentum table first. Give it a try and see if it'll help you. Sometimes I think the organization of it is super nice. So here we've got a 0.5 kilogram red billiard ball moving at 2 meters per second to the right, and it strikes a stationary 1 kilogram blue billiard ball. After the collision, the red billiard ball is moving 1 meter per second to the left. What's the final velocity of the blue ball? So to do a momentum table, what you want to do is make two columns, one for P initial and one for P final. And then as the rows, you're going to list all of the objects. So I've got the red and I've got the blue. And then we're going to also be dealing eventually with the total momentum as well. So red, blue, and total. So red beforehand, it says 0.5 kilograms moving 2 meters per second to the right. So what I know I'm going to put in there for the red one, 0.5 kilograms times 2 meters per second is 1 kilogram meter per second. So I know I can put in here that the red one is going 1. And the blue billiard ball is stationary. So 1 kilogram times 0 is just 0. So the total momentum beforehand is 1 kilogram meter per second. Now, for the final momentum, I know that after the collision, the red billiard ball is moving 1 meter per second to the left. So I do need to account here for the direction still. So I've made right positive over here. I made that positive. So we're going to say afterward, the red ball, it's going to be still that 0.5 kilograms, but now it's moving 1 meter per second to the left. So its momentum is now negative 0.5 kilograms meter per second. And that is just capturing the fact that it's going to the left. And then finally, I want to know the blue one. So we'll go ahead and put in the numbers here. Its mass is 1 kilogram. So it'd be 1 kilogram times the final velocity, which I don't know. Now, what you do here to get the total, you just add it up. So this one would be VF minus 0.5. And then what you can say here is that momentum has to be conserved. The total column has to be the same. So I know 1 has to equal VF minus 0.5, and thus the VF is 1 plus 0.5, 1.5 meters per second. And that ends up working out. Now, if you don't like using the momentum table, you can just use that really long equation. I'm going to go ahead and list out the equation here. M1 VI1 plus M2 VI2 equals M1 VF1 plus M2 VF2. So to use that one here, you're going to plug in those same numbers that you had, which are 0.5 kilograms for the first ball, and it's moving 2 meters per second. The second ball is 1 kilogram, and it's moving at 0 to start off with. And then afterward, the red ball is 0.5 kilograms times its final velocity, which was negative 1 meter per second, because remember, it's moving to the left. And then finally, 1 kilogram times VF2. And so you start solving that out. 0.5 times 2 is 1. That's just 0. That equals negative 0.5 plus VF. And you'll notice I get the exact same answer. So either of those methods is perfectly fine, whatever kind of makes most sense to you. Okay, to wrap things up then for this video, I've got 6 practice questions that you actually could do here. I don't want to make you watch a video of me going through all of these questions here. So what I figured I would do instead is go ahead and just tell you the answers, and you can kind of check your work as you go. So you can do them however you'd like, and then if you need any help knowing how I got these answers, come let me know, and we'll go from there. So for the first one, I solved and got a final velocity of 5 meters per second. For the second one, I got a final velocity of 0.2625 meters per second. That one you got to be a little careful with the lefts and the rights there. For number 3 here, I got 2.35. meters per second. For number 4, I got 2.81 meters per second. Now, number 5, I did want to go over. So if you're still watching and you've done number 5, this one is a little tricky here. So one mean thing they've done is they've given you the force of gravity. So to get the mass, you'd have to use Fg equals mg. So 730 newtons equals mass times 9.81 meters per second squared. And when you get this mass here, I believe you get 70 something. Yeah, 74.4. Once you end up getting that 74.4 kilograms here, this is a little bit easier. This is an explosion. So one thing I like to do with the explosions, if you're using that big long equation, M1 VI1 plus M2 VI2 equals M1 VF1 plus M2 VF2, since neither of them are moving at the start, both of those are 0. So explosions are kind of nice that way. Then for the other two here, I'm going to get M1 and VF1. So the mass of the student is 74.4 kilograms. And I want to find his speed or her speed. And then M2, it says the textbook is 2.6 kilograms. And VF2 is 5 meters per second. Now, I obviously made the student the first one, but you could have done it either way. So 2.6 times 5 is 13. So 0 equals 74.4 VF plus 13. And when you solve that out, you're going to get VF to be negative 0.175 meters per second. The negative, of course, just telling you that they're going the opposite direction as the book. Now, this didn't tell you the answer, though, because I got to find out the time it's going to take. So I would use D equals VIT plus 1/2 AT squared. Now, the nice thing here is the student isn't accelerating. They're just moving at that speed. So to get your time, they move 5 meters, and then it's 0.175 meters per second times the time. And I get a time of 28.6 seconds. So this person is not moving very fast. For this last one, then number 6, that's a more traditional kind of explosion question here. The only tricky thing here, again, is they've given you the newtons rather than the mass. So it's 74.4 kilograms again. And just to do this one really quick, because I don't want to run out of time here, I got an answer here. It looks like the student to be 8.1, a little bit of rounding, meters per second. Okay, folks, thank you guys so much for watching this video on conservation of momentum. Have a fantastic rest of your day.